Yes, so I'm from Center of New Technologies, although I'm quite far from providing new technologies, except maybe for some basic experiments. So today I will present some results that I realized during last years, like with the title, general title, like Quantum Chemistry Chemist Perspective on Ultracold Atoms and Molecules, and I would like these two examples will be kind of example how quantum chemistry and quantum chemists in general can provide input for ultracold physics of ultracold atoms and molecules. Although in general I feel more physicist, so it's like sometimes it's problematic. I feel like to be a bit superposition of quantum chemists and quantum physicists. So depending on the community, probably for physicists I'm more chemist, for chemists I'm more physicist. Okay, so first maybe why ultracold atoms and molecules are interesting. I think that here there are a few people working on this field, so probably this was justified many times, but just to mention a few the most important applications, not so much related to quantum technologies yet, not to technologies yet, new technologies. So one of them is precision measurements and test of fundamental laws that can be realized with such systems. Quantum simulations of many-body physics is another very important goal, both for atoms and molecules trapped in traps or in optical lattices. And the other part that is probably one of the most interesting for quantum chemists is ultracold controlled chemistry. So it's chemistry at very low temperature in the quantum regime, where we can maybe learn something useful also for higher temperature chemistry. And as I mentioned, I will present two separated topics, like two parts. And in the first part, I will present ultracold isotope exchange reactions between heteronuclear dimers in external fields. This is the proposal of new experiment that I published some time ago. And I hope that at the end, it will be clear for everyone what do I mean by this kind of reactions and why it is interesting proposal, and hopefully why it will be realized in not so far future. So what do I mean by isotope exchange reaction? So I consider that we have ultracold gas of heteronuclear molecules like this, consisting of two different isotopes of the same atom. So we can write it like this. So we have heteronuclear molecules in the ground state that consist, for example, from rubidium-87, rubidium-85 atoms. Then they collide. And then the question is this kind of reaction possible? If it's possible, what is interesting in this, and what can we control it, or can we use it for something? So now, before I will go to the details of this specific. Yes.
Is it, since I'm not a chemist, is it very difficult to manufacture this different molecules?
So it should. Yes, so the idea to produce them would be the same as it was with other alkali dimer molecules. Like the first molecule that was produced in ultracold community was potassium rubidium molecule, and it was realized by combining two clouds of cold atoms, then magnetoassociation. So it's like applying magnetic field to associate molecules.
Gas of one isotope and
Yes.
I mixed them.
Yes, but then you have.
How probable is the molecule which forms is heterogeneous and not ordered?
No. So because it does not happen spontaneously, so you have to apply some kind of formation scheme. Yes, and you can
How difficult is it?
So you can selectively produce. So it's like when you apply the magnetic field in the right value, and then the proper laser fields, then you can selectively produce only heteronuclear molecules, because the homoatomic pairs will not feel. For example, the laser field that are used to transfer.
So
Because
you can manufacture.
yes, because I can maybe write like.
It's okay. The question is that
No, but I mean, it's like the idea is that you use magnetic field to make very weakly bound molecules that are of huge size, and then you apply laser field in this kind of scheme like this. So once you produce these molecules, even if you produce weakly bound molecules of all possible mixtures, then when you use the some given frequencies of the lasers, you can selectively produce only the dimers that you want. So
I can take the two isotopes, mix them, and what comes out is the gas consisting of
yes,
the left side of your picture.
yes, it should be possible. Of course, this experiment. No, it is possible. I mean, it can happen because, of course, always it can be something, some kind of, I don't know, unexpected features of this kind of mixture. But for sure, you can find the different, some atoms, some isotopes that it's possible. This is for sure. But it's experiment. This kind of experiment would take, like, let's say 2-3 years if you start from zero. So of course, this experiments with ultra-cold atoms and ultra-cold molecules, they take time. But
A short, similar question. Is it thinkable that this reaction could possibly go in other direction?
so this is one of the this is one of the questions that I ask. So first, let's assume that we have this.
You plot arrow in one direction.
Yes, but at this slide it should be yet with the question mark. So it's not yet decided. But in the talk I will answer if it's one directional of.
Because it's interesting for some reason. Is it possible to manufacture heteroisotope, I mean, with different isotope molecules for all possible systems? For example, we know that the hydrogen is the simplest molecule, right?
Yes.
Manufacture a molecule, deuterium normal.
I mean, these molecules, they are done, I don't know in what kind of way. Probably they are produced in the way as they produce hydrogen, but they just have all isotopes and then they select. But with ultra-cold hydrogen is very problematic. So we can produce this for sure for alkali atoms, but somehow we are restricted to the atoms that are used in other ultra-cold experiments. So of course,
Even hydrogen has been already condensed.
yes, but yes, it's possible, but
Deuterium normal.
it.
I don't think deuterium was condensed, but hydrogen, yes.
Yeah, I'm asking whether
Yes, you can buy it in the shop.
molecule of a
HD.
HD, yes.
Which one atom is a deuterium, the other is normal, or a tritium, deuterium, or whatever. That was the point, not whether you can that time.
Yes. So if you can reverse this reaction, this would be a possibility to have H2 and D2 and go in other.
So HD you can buy in the shop in the bottle. So it's like standard industrial thing. But then, of course, it will be. This is quite specific case. But okay, so this is general idea, and now let's go to even more general picture of chemical reaction. So what do I mean by chemical reaction? So I have some two reactants like AB in my trap or flask. Then I have some collision energy, so some temperature of the system, and then reaction proceed. And depending if the reaction is exoenergetic or endoenergetic, then the additional energy can be released, or the energy of the products can be up. And then, of course, some products are possible. And when we are at room temperature, at high temperature, then, of course, the problem is that we can have really lots of quantum states of the reactants, because we have at room temperature many vibrational states, many rotational states, and many other degrees of freedom of molecules can be populated. So once we start with the room temperature sample, it's like quantum description is not needed, because like thermodynamics or statistical physics describe it much better. Or okay, maybe some quantum is like input really at the bottom, but there is no visible way to apply, for example, quantum control to this kind of systems. And then, of course, if the additional energy is even released, then even larger numbers of quantum states of possible products is possible. So starting from this kind of reactants, we can produce even larger number of possible states of products. So it makes it start to be problematic if we want to have some control, or we want to have selective transitions. So the dream for chemists, for organic chemists or any industrial chemists, would be to start from some selective products, some selective reactants, some chosen molecules, and then to produce the products in very given quantum state. And now there is still not a clear idea how to do it, but with ultra-cold reactions, maybe we can learn how to drive this transition from selected quantum states of reactants to some selected quantum states of products, and then hopefully, for example, to increase the yields of the organic synthesis.
Your area of interest is the energy release in the form of collision energy or photon.
It can be in different ways. So, yeah, in the case of chemical reaction, it will be rather collisional energy plus the internal energy of rotations and vibrations. So, let's say in general, yes. In this kind of we don't have radiation, because let's assume that this kind of energy release is very small, so the wavelength would be very yes. It's it's always. There always
finite lifetime.
Yeah, of course. So for many systems there will be this kind of mechanism, but for the typical chemical reactions it's not important. But of course there are like other reactions like charge transfer or something like this, and we are interested also in ultracold reactions where the light is important, but it's not important for this presentation and what I'm considering here. Okay, so we have this picture. Some quantum effects can come when there are some barriers for the reactions, because then of course tunneling is needed. This is more quantum effect, and then, but in principle, it's not general. So how to add some quantum to chemical reactions? So this is what we are doing in ultracold community. We decrease energy, collision energy, because once we go to ultracold temperatures, once we go to milli or microkelvin temperatures, we can be in the regime when we have our reactants, our initial molecules or atoms, in really just few or even only one quantum state. So by decreasing temperature, we can really produce the system in some very well selected quantum states. And of course, hopefully, the hope is that once we go to this regime, we can gain some control, some quantum control by controlling some quantum reflection or tunneling over this system. But once we look on these general pictures, and if the reaction is exoenergetic, we can see that still the energy released in this kind of reaction can be many orders of magnitude larger than the initial collision energy, and still thousands or hundreds of thousands of millions of quantum states of products can be produced. And is this the problem or not? So when we look on very simple model, like the simplest possible model that someone can imagine for chemical reaction, we can ask what is the probability for the transition from some alpha state of reactants to some beta state of the products. And it can be written in some very simple form, where this kind of probability for this kind of chemical transition is given like by the probability of the capture of reactants in the channel alpha, multiplied by the probability of formation the intermediate complex in the beta channel of products, divided by all possible other channels. But now, when we are in the regime, when we have in the ultracold regime, when we have only single entrance channel and many exit channel, we can ask about what is the total probability for the chemical reaction to happen. And once we make a sum over all possible product states, we see that this sum over beta is sum over gamma without alpha. So in fact, the probability for the total reaction is simply proportional to only to the probability of capturing the reactants. So we can see that in this very simple picture, we don't have any information when we look on the total rate of the total rates of chemical reaction. There is no information from what's going on in the products. So only for the total probability of reaction, and for all other information, only what's going on in the entrance channel is important, and the product channels are just kind of reservoir that is collecting whatever happening in the middle. Okay, and how far it's from the reality? So once ultracold molecules were produced, and the first ultracold molecules that were produced were potassium, rubidium in July in 2008, and they realized few experiments. So they shown that in fact, once we have our chemical system at very low temperature, then lots of quantum control can be gained. So for example, they started from preparing fermionic molecules, and by controlling if it's identical or distinguishable fermionic molecules, they observed or huge suppression and proper scaling with the temperature of the rates, or very fast rates if the fermions are distinguishable. They also changed the other atom that collides with the molecule, and depending on the energetic of the reactants, reactions were faster or weak or slower. They also applied some kind of traps to reduce dimensionality or electric fields to control the reactions. But in fact, if we look at all this control is happening only in the entrance channel. So they only control the quantum states of reactants, but not of the products. So there is no information on what is going on with the products of this reaction. And in fact, it was, for example, Zbyszek i Jaszek with Paul Julien, they suggested a very simple model to describe this picture. In this model, they only assume, that when molecules are very close to each other, then they are lost, and there is no information from the product. So there is no flux of information coming back from the reacting complex. So once the molecules are together, the system does not know anything about what's going on in the system and where the losses.
Talk about this possible ground state. Do you also mean that rotational energy is not present?
Yes, we assume that. Yes. We assume that it's in the ground state, but this can be controlled. So it can be both the hyperfine state of the molecules, like the spin of the nucleus, can be controlled. The rotational structure can be controlled. So we can produce once we can produce this molecule in the ground state, we can also excite it to any rotational or vibrational state that we want. Okay, so we have this first ultra-cold chemistry that, as it was shown by Zbyszek i Jaszek, it's quite universal. So what about products? So once we look on the products of this reaction, of the reaction between potassium-rubidium molecules, we can see that in fact thousands or even tens of thousands of possible quantum states of products. These are rotational and some vibrational states presented. And now the question is, if we apply the electric field, can we control this kind of product distribution, or can we measure this, or can we control selectively the transition from our initial state to some given output? And unfortunately, in this regime, when we have much larger number of possible states of products, this control is not really feasible because of these statistics that I have shown at the beginning. So the authors of these papers that apply electric field, and they observed some kind of difference between these two distributions, but this is definitively not measurable in any experiments because the difference is too small. It's much below the error bars. So the question is, can we find some better system to realize the chemical reactions where the product distribution can be controlled, or some flux of information from what's going on with the products will go to the.
Are these peaks real, or this is some kind of?
This is in the probability. So this is kind of arbitrary units, but it's relative probability for producing states of the products of this.
Is this experiment?
No. This is theory. This is theoretical. Yes. So until now, just to mention, yes, until now there was no measurement of the product state distribution for any ultra-cold experiments, because first of all, the energy release here, although it's just a few wave numbers, so this is in kelvins, it's around 12 kelvins too. So although this few kelvins is very cold, it's too hot to be trapped, because our traps, they have the depth of our traps is millikelvin regime in best. So we can only trap very few products here, and because also the number of these products is so large, it was not yet measured. So this is the reason, and this is motivation for my work. Let's find some system when we will have smaller number of products, and products that can be trapped in our experiments to be detected and to measure relative probability for different products formation.
For the situation where the released energy is very small.
Yes, very small, much smaller, that the products are still in trap, and the number of products is much smaller, and then I hope that there will be some flux of information back, some kind of resonances in the products. Distribution will be important also on the total reaction rates. And okay, so now a few years ago, Piotr Żuchowski with Jeremy Hudson, they look on the energetics of the alkali dimers, because alkali atoms were the first used in these experiments. They look on the energetics, and what they found, that in fact the potassium-rubidium molecule is actually the best among what it can be done, because the energy release is the smallest one about the reaction, about the dimers where the reaction is possible. So looking, this is wave numbers. Yes, but so it's. No, it's wave numbers, yes. So it's few kelvins up to few hundred kelvins. Okay, so this is the best system, but it's still not the one that we want. So then with Roman Krems, I also looked on the dimers in the triplet state, because when we have two alkali dimers and we produce the molecules, we can have both singlet state molecules and triplet state molecules. And the idea here was, okay, maybe if we produce the molecules in the triplet state, then we applied external magnetic field to confine the dynamics to spin stretch state, to the state of the state of two molecules with the highest spin. Maybe we can keep the system in this surface, and then maybe energy release will be smaller. And in fact, we found that yes, the energy release in this kind of reaction is smaller. For example, for potassium cesium, it's order of magnitude almost smaller than for potassium cesium, but potassium rubidium that was presented in the previous slide. But unfortunately, we found that for the molecules in this triplet state, always the losses due to the trimer formation are present. So even if we have just a very small energy release for this simple reaction where the atoms change position, like from heteronuclear to homonuclear, then always trimer formation is possible, and we have losses. So this is not the solution. Okay, so now let's go to this isotope exchange reactions, and let's ask if this arrow is right, and what is the energy release in this kind of reactions. And just by making very simple approximation at the beginning, starting from zero point energy in the harmonic approximation of the potential, we can show that the energy change, the energy release in this kind of reaction is given by this simple formula. And what we can see here, first of all, it's negative. So negative in my convention means that the reaction is possible, so the reaction is exoenergetic. So it means that reaction goes really from that the reactions go from left to right. So this is the direction of the reaction. And what else can we see here? That this term is much smaller than omega 0, where omega 0 is the lowest, lowest vibrational excitation of the system. So it means that this energy is much smaller than the first vibrational excitation of the products. So it means that once this reaction happens, then the products only in the lowest vibrational states are possible. If some rotational excitation are possible, we can check by comparing this number to the rotational spectrum of molecules.
So those two numbers M and N are equal, and the energy difference is zero, and the reaction can go in both directions.
Can always go in both directions.
Yeah, okay, but the probability, the comparable probability.
Yeah, but if it's like, because this is mass of the one isotope and the other. So if we have like rubidium with the same isotopes, so you cannot distinguish which side of the reaction you are. So if you start from the ground state, then yeah, if it happens, you somehow, these are identical fermions or bosons, so you don't know if you exchange boson or not.
The isotope, this difference is just the number of neutrons.
Yes.
How much is it?
There are two different, two, because it's.
So it's 4. So this number is 4.
Yes, this number is 4 here. Yes, divided by the reduced mass of the molecule, when this is quite large prefactor, so it's really small, very tiny part of the lowest vibrational excitation. Yes.
But directionality here means only that you have many more atoms which are there.
Yes.
And very few, so this is just
Statistical flux going in this direction.
Yes. So of course, if
they go backwards also, but there are very few.
yes, at the beginning.
The probability of going backwards is much smaller.
Yes, because the total rates is proportional to the square of the density. So of course, if at the beginning you don't have any products, then most of the reaction will go to the right. But of course, if you have equilibrium, at some point there will be equilibrium, and if this is what is observed in any room temperature. Yes. Okay. So and then I put the table exact energy release in this kind of system by diagonalizing full Hamiltonian for the molecules, and what we can see that the energy released. This is the the data that I want to present in this table, that the energy released for these dimers consisting of alkali metal or alkaline earth metal, they are in the regime of, let's say, tens of megahertz, only for lithium because the reduced mass is much smaller, it's much larger. And when we compare the energy in megahertz to millikelvin, we can see that 20 megahertz is around 1 millikelvin. So it means that the energy released for this kind of dimers is in the range of few millikelvins, or for some of them, like strontium-strontium or ytterbium-ytterbium, it's even below millikelvin. So it means that the products are already in ultra-cold regime, because our definition of ultra-cold is below 1 millikelvin, and that our traps that can be used for trapping these molecules, they can have depth up to few millikelvins, maybe sometimes even. So already at the beginning, we are in the regime where we can hope for trapping the products. And now when we compare this energies released to the rotational constant, we can see that rotational constant is much, much larger. So this means that for this kind of reactions, only if we start from the ground state, both rotational and vibrational ground state, that no rotational or vibrational excitation can happen in products. So in fact, when we neglect the spin of nuclear, then we just have one single product channel. So we have reactants, and then only single quantum channel states of products are possible. And
is there observational confirmation of your calculations?
Not yet. I mean, these numbers are based on experimental data. So
Yeah,
it's.
but they are based on data, whether they are directly checkable by experiment.
I mean, they are.
Because they come from, yeah, I understand, diagonally.
Yes, but they. So what I'm using? So I'm using the potential interaction potential for these molecules that were obtained from the spectroscopic measurements. Yes. So they have spectroscopic accuracy. So these numbers, they are spectroscopically accurate. They are as accurate as the measurements for this kind of molecules. So these numbers are sure, and I mean the error bars here can be given, and they are below probably few percent of it. So these numbers are for sure true, because they are based on the experimental interaction potential. And then diagonalization of the vibrational states of the simple diatomic molecules is exact in the way that there is no numerical error in this kind of procedure. Okay, so we have this simple energy released, and can we do something else with this? And this is the idea that, okay, we have the energy release. Can we control? Maybe because this is I shown for the results for the potassium rubidium molecules, and potassium rubidium molecules it has a dipole moment, and lots of control was presented by applying electric field to control the chemical reactions by aligning the dipoles or changing the rotational states by aligning electric field. So then the question is, can we control this kind of reaction in similar fashion? And unfortunately, homonuclear molecules, they don't have dipole moment. In fact, there is very, very weak dipole moment due to breaking the symmetry, because there is not the same atom, so there will be very, very tiny dipole moment.
Change in the center of.
Yes, due to breaking the Gerade-Ungerade symmetry. Electric dipole moment, yes, but electric dipole moment. So it will be very slow. It will be very, very, very little. So I think for the HD, it's I think like 1/1000th of dBi or below. So maybe it's even 1/10,000 dBi. So it's a few orders of magnitude smaller than what is for potassium rubidium, and this is too small number to be useful. But then I found the control scheme by applying the Stark shift, but with the laser field. So applying the dynamic Stark shift. And the idea for this is quite simple. So in this picture, I presented the electronic states with the raw vibrational states for the ground state of our molecules. So this is the ground state of our initial heteronuclear dimers, and these are some excited states. And when we have the different reduced masses, then this energy is slightly different. So there is some difference because the vibration of the diatomic of two atoms in the well of the interaction potential depend on the reduced mass. But then when we look on the higher excited states, like some highly or not highly, but in the middle of the well vibrational states in the excited state, then this difference here propagates to much larger numbers. And now, if we are able to find the situation where we can apply some laser frequency that is close to be resonant with some transition for one of our isotopic mixtures, and is off resonant for other, then we can have the Stark shift only for this kind of transition which is close to the to this laser frequency, and it's completely not visible for other molecules. And in fact, this kind of condition can be easily found for most of the molecules that are used now, so most of the alkali dimers. So in fact, for all of them, but it can happen that, of course, somehow accidentally for some chosen transition, it can happen that these three laser frequencies are resonant, but it will be only some kind of accidental coincidence. And in general, we can always find this kind of transition. And now when we apply this resonant laser for the heteronuclear dimers to have the stark shift for the reactants and no shift for the products, we can relatively tune the threshold of these products and reactants, and this is the stark shift shown for these heteronuclear dimers, and it's in the language of like Rabi frequency, in the language of the line width of the transition, and we can see that we can induce the stark shift, the dynamic stark shift of the order of few line width of the transition when we apply the Rabi frequency that is in the same order. And in fact, because the line width of this transition for heteronuclear or homonuclear alkali dimers is very similar to alkali atoms, and it's in the range of 10 to let's say 40 megahertz. So it means that we can easily induce the stark shift that is in the range of tens of megahertz. And when we look on the table, this was the energy release in the reaction. So it means that we can apply stark shift, the differential stark shift different for products and reactants, that is in the order of the energy release in the reaction. So it means that once at the beginning we were starting from the products with the higher energy and reactants in the lower, once we apply the stark shift control in the proper way, when the tuning is the right direction, we can tune the energy release in the reaction, even leading to the suppression of the reactants. So if we push our products with stark shift down in energy, then the reaction can be suppressed. So in this way, we gain the control over, first of all, the energy release in the reaction, and second, we can even suppress the exothermic reaction to become endothermic one.
What is the intensity of these lasers here?
Yes. So this is the next slide. So in the next slide, I shown the Rabi frequencies needed for this transition. And the Rabi frequencies needed for this transition, there are in the tens or hundreds of megahertz. So this Rabi frequency is absolutely in the regime that can be achieved in the experiment. Okay, so we have this kind of control, and can we apply some additional control? And the answer is yes, because we can apply magnetic field, and we also can have Zeeman shift connected with the spin with the nuclear spin. So we don't have electric spin in closed shell rubidium molecule in the singlet state, but there is always for alkali dimers the nuclear spin. And when we look on the order of magnitude of this very tiny Zeeman shift, because Zeeman shift for the nuclear spin is very, very small, but still it's in the order of megahertz. And this is exactly the scale that we need to control our system. So if we apply the magnetic field in the range of few hundred or thousand Gauss, we can induce few megahertz of the shift, and in this way we can have additional control over the relative channels on, or now we can split our hyperfine states of the molecules if there is nuclear spin into many Zeeman channels. So starting from the case when we have one quantum state of reactants, one quantum state of products, we can split the number of channels, so we can have additional control. We can increase number of product channel, or we can also start from some selected quantum state of the reactant. So this is additional tool to control.
So chemists are still using illegal units of
It's illegal. So I mean, these units are used by physicists. I haven't seen the.
Astronomers use.
Yeah, and also physicists.
I mean, in Ultracold community, I mean, probably 99% of. Tesla is too big, because Tesla is 10,000 Gauss, so it's. No, it's. Yeah, so this is quite, especially that quite. In fact.
Very often.
Yes. In fact.
With bees which are less than a few.
Yes. Because in fact, 1,000 is like the limit where it can be controlled quite well. So probably the best fields that can be applied is maybe few thousand, but realistic system that never more than 1,000 is used. And in most of the system, we want to use few hundred or even less Gauss. So then it starts to.
What do you mean control?
Yeah.
Control the
Yeah. Of course. Yes. In our experiments, I mean.
Otherwise, we will all be dead after nuclear.
Yes. Of course. The question is that it's quite challenging to combine very strong fields with our machines, because of course I don't have any machine, but in the machines that are used for this kind of devices, yes, for this kind of experiments. So, okay, now how can we combine all this information to get some knowledge about chemical reactions? So, okay, we can start from rotational excitations of the system to control the number of rotational states, because if we apply some rotational excitation, we add the energy to the system, and we can in this way control the number of exit channels of different number of rotational exit channels, from one to several. We can also excite vibrationally our heteronuclear dimers, and once we excite it vibrationally, we provide like tens or more kelvins. So it means that we can directly go to the regime when the reactions are universal, because thousands of possible rotational states is possible. We can apply the Stark shift control to tune continuously the reaction energy from tens of megahertz to 0. So in this way, suppress exothermic to endothermic reaction. And finally, in all this picture, the most important message is that we can have quantum control of reaction rate by controlling the product state. So it was not yet observed or proposed in any other experiment where this quantum control of reaction is obtained by controlling the product state. So we can imagine that we can observe in the total rate of the reaction not only the resonances or tunneling in the entrance channel, but also the impact of quantum statistics, Wigner threshold laws, shape resonance, interference, quantum tunneling, and many other in the product channels. So this was not yet observed, and this is like the most important message of this proposal. And finally, still there is not too much knowledge about what's going on in the middle of the reaction, because once these two molecules that are together, there is intermediate complex, there is some complicated dynamics, four-body dynamics, and the idea is once we have very simple system, then maybe we can learn something interesting about what's going on in the middle. Like if, for example, there are some conservation law of some momenta, for example, that are not strictly given by laws of physics, but for example that the nuclear spin is not so strongly coupled to rotations, and maybe the nuclear spin can be conserved during this kind of reactions, and then of course the reaction, the distribution of the products and total rates will be different. But this is what has to be done in the more exact calculations or in experiment. But as I mentioned, yes, so producing the heteronuclear molecules for this experiment can be challenging, and it can take 2 years from now if someone starts, and no one probably yet started, or no one informed me that started it. But the same idea can be, in some modified version, can also be applied for some heteronuclear molecules when we just combine it with the atom that is other isotope of one of these atoms. So then the question is, what is energy release for this? And we can find the systems, for example, like potassium sodium, where the energy release, okay, it's not so small as in my proposal. It's at the beginning 400 millikelvins. And in fact, this does not include some other effects like isotopic effect connected with the nuclear spin and or nuclear size, but it's in this kind of range. So then not only one product state is possible, but few of them. But this can be already done at in some labs in the world. So for example, this kind of isotope exchange reaction is already in progress at MIT in the Martin Sphere-Line group. They are interested in realizing this kind of experiments. The other group that is working in this kind of system, when we have the isotope exchange but between molecule and atom, is in the Doi group, where they have strontium fluoride and they mix it with different isotope of strontium. Okay, now I would like to sum up the first part that already took more than half of the time, but I mean, I think I told most of this, that I proposed this I proposed isotope exchange reactions for some interesting exploration of chemical reactions in the quantum regime of ultra-cold temperatures. Okay, so I think I can still continue, right? For how much time do I have in total? 20 minutes. Okay, then in 20 minutes probably I can give some story. Okay, now in the first part I presented the quantum chemistry approach to ultra-cold collision or ultra-cold systems when we look on the molecular, on the structure of the internal structure of molecules, and this is one of the huge applications.
Consider the first part of your talk. If I have this isotopic molecule, do they interact chemically different than
No, the point is that it's like quite good approximation is to describe the dynamics of different nuclears on the surface of the electronic states. And this electronic surface is very similar. There are some corrections that are mass dependent, but in general they are very, very similar. So answering your question, at room temperature, these differences are completely negligible. So they
Not like this, that is different isotopic molecules interact differently with something.
I mean, in principle, it's very. It can.
Do they exist in the real nature?
I mean, yes. For example, this is like you can ask about oxygen in the atmosphere. So there is oxygen produced like the oxygen 16. No, but it can happen that like oxygen 16, one atom in the molecule is converts to oxygen 17. I don't know the numbers, but of course it's.
How do you know they play any role in nature?
I mean,
Statistically, essentially,
no, they.
exist.
No, this is.
I'm not asking about exist. I'm asking whether they play any role.
This about the rule.
That's a different thing.
About the rule, it's hard to say, but for sure they exist and they can be.
Not that we rule out the water.
Yeah, but I think that, for example, it can still be important in biological systems, because if you take different isotope of some atom, it can happen that for some specific, I don't know, proteins, it can fall different. I don't know exactly, but I don't know if this can be the effect. But it can potentially. But I mean, I don't.
We know anything
Same
about
ballpark as isotope shifts.
Yes.
They are tiny, of course, and the heavier the atoms.
They're different. Yeah, exactly. So, I can imagine. Yeah, I think that probably for example, it can happen that for the like hydrogen bonding, it can happen that it can be much different if the deuterium is used instead of. But yes, it's hard to.
You just said that there is no.
No. The point is that then it can happen that because the mass is different, so the dynamics, the dynamics is different.
Out in the discussion, the hetero.
No. I mean.
Heteroisotopic water. I asked at the very beginning whether there is the deuterium normal hydrogen.
No.
Hydrogen molecule exists.
Yeah. No. It can exist in the way that, but
It can exist. That everything can exist. But
no. It exists in the way that you look on the number of deuterium.
Numbers, the probability of
You
forming.
mean like semi-heavy water? Of course.
HDO.
Heavy water is something
Yes,
very
right.
different. It's the same deuterium with the oxygen.
Yeah, I
The
understand.
heavy water is well-defined object at least. So that's
Yeah,
the
sure,
first.
sure.
Then
So-
stick to it.
No, but for sure you can I think produce
The
the.
answer was that the numbers are I fully agree that somewhere in this huge uniform universe there is a heteroisotopic water.
Yeah, so I don't know what is the
question was,
probability.
Yeah, I understand.
That its presence,
Yeah.
statistical presence is ruled out by this number. So I was just
The
asking
numbers-
whether
the
they
numbers are some.
Normal reactions are. The answer is that nobody knows.
No, I think that some people knows, but it's not important for us, and I didn't look on
We
the
don't
water.
know, we don't know.
Yes. Okay.
So statistically, nobody.
Okay, so in the second part, I would like to present a bit different approach of quantum chemistry. So applying the quantum chemistry methods to investigate the atoms, but where the atoms are treated as our quantum particles. Because like the 99% of work of quantum chemistry is solving the Schrödinger equation for electronic systems. So we try to find the wave functions for the fermionic systems of electrons. And in fact, when we want to work with the ultracold experiments with Fermi atoms, they are in fact very similar objects, because the internal structures of ultracold atoms is usually not important for many body dynamics. So we ask, can we apply some quantum chemistry methods that were developed in the last 50 years to successfully solve the electronic Schrödinger equation for solving the Schrödinger equation for fermionic atoms in traps? And some motivation for this kind of works is because in the last years it started to be possible to produce just few Fermi atoms in traps in a very controlled way. So it was possible to produce 1, 2, 3, or 10, or any number in any number of atoms in trap. It was also possible to produce in 1, 2, or 3D. So we started from 1D and applied our methods to this. So the result of that I presented is the result of collaboration between groups of Maciej Lewenstein at IKFO, where I was postdoc, and Robert Moszyński here at chemistry department, and I work with Robert Moszyński's PhD student Tomasz Gryning, who did most of these calculations. Okay, so let's start from the Hamiltonian. The Hamiltonian for our Fermi atoms in the trap, like structureless spin 1/2 fermions in one-dimensional harmonic trap, is like this. So there is kinetic term, the trapping potential, plus the interaction that we assume that it's given by the contact interaction with some G coefficient. And this contact interaction is only for the different fermions. So in fact, for fermions up or down, this interaction is only between fermions up and down. So the same.
Where is the spin in this?
I mean, the spin is somehow included in the way that we assume that this interaction term is only for states with different spin. And then like we...
So it could be expressed in the second quantized?
Yes, it can be expressed in the second quantized, and somehow here we induce the spin, we include the spin by the form of wave function, that if we look...
So the n is the number of the total?
Yes, total number of particles, yes.
And half of them is spin down and high?
In general, yes. In general, I mean, we start from the... In general, you can assume any number of it, but we start from...
Then how, if you don't know how, then you write the G?
No, the G is between up and down. Between two atoms, one up, one down.
Why the sum is on over?
I mean, the sum is that
I
if...
don't understand how you distinguish between the spin and force.
Okay, so, yeah.
I mean, how do you distinguish?
Yeah, so we should...
What is meant by I
This is
less
seen
than-
in the wave fund. You do not see it here in the wave fund.
Yeah, so I should add the projection
I agree
operator.
that this is not written in the proper way, because
Okay,
if the
okay.
sum is supposed
All right,
to
now-
run over all I
No,
and
no,
j,
it's-
provided j is bigger than I, then
It's
it is
okay.
wrong.
Yeah, so...
Now we know
Okay, so we understand
what's going
Yes, so I should add here some projection operator to make it more clear, or write it down in the second quantization form that it would be more clear. But this is, I think this is quite standard Hamiltonian that was solved for many ways. So like the solution for two atoms were given here by Professor Różewski, and of course it was, as was mentioned by many people here, explored. But we wanted to look on this from the quantum chemistry perspective. So now, how do we solve the many-body problem? So in quantum chemistry and in many other approaches, we define some set of one-particle functions. And once we know that once we have the set of one-particle functions that spans the one-particle Hilbert space, then we also know that from this kind of basis set we can construct the basis set for the many-body functions, and this will be also complete. So if we construct all possible n-particle determinants from this one-particle functions, then we know that this set also span the total Hilbert space. So this way we can potentially. Yes, this is but now this is the problem, that of course the number of possible possible n-particle determinants start to increase like exponentially, or in fact. So this is the problem. So then always some kind of approximation has to be applied, and this is what is the center of quantum chemical approaches, to develop different methods to truncate the wave functions once we describe electrons. And here we use the same methods with the same wave function representation to describe Fermi atoms. And of course, once we apply this, the name is algebraic approximation, where we cut the basis set of the one-particle functions, because we can have both not complete set of one-particle functions. This can be one source of error, and the second can be that we have also to truncate the basis of n-particle determinants, and this is the source of other the other source of errors. And of course, then the results will depend strongly on this cutoff of the number of one-particle functions and the analytical structures of the one-particle functions. Because if we choose it properly, then probably the results can converge faster with the number of used basis sets.
Are you trying to get only the ground state or also the excitation?
In general, we want to all states, also excited states. So of course, if we go to higher excited state, then we have to include larger number of one-particle functions, and it starts to be problematic. Okay, so because we wanted to make like kind of tool example, we applied just a very simple single particle function. So we use the harmonic oscillators because it's 1D problem. And then what we find, we shown that we rigorously analytically shown that for two-body Hamiltonian, the energy in this kind of basis set making the exact diagonalization converges to the exact results in this way. So with the number of used one-particle basis sets. So this is very, very slow convergence. So this is 1 over square root of number of basis set particles. So it's extremely slow convergence. So it means that we have used really huge number of one-particle basis set to get really converged results. And of course, the problem is that our calculations, they scale they scale exponentially with the number of single particle functions. This is the problem. And we also shown numerically, not analytically, that the same formula also apply for a general n-particle system. Okay, so knowing this, we applied two methods of quantum chemistry. So, I mean, full configuration interaction method is just general method that is applied to any many-body quantum system. So we can expand the total wave function in the all possible stated determinants. So this is just expanding the total wave function in all stated determinants with some coefficients that can be defined variationally. So once we diagonalize the Hamiltonian in the basis of all stated determinants, we can find the energies and we can find the exact solution in given basis set of one-particle functions. If this set is complete, if it span full one-particle Hilbert space, then our result is complete in the n-particle space too. But as I mentioned, this kind of expansion is exponentially hard, and we can go to 6 particles maybe easily. To 10, it will be really only in small basis sets, and for more than 10 particles, it's usually impossible to get any results with the full configuration, with the exact diagonalization in the complete basis set of n-particle stated determinants. So,
and the base that you were using was still the empty harmonic.
Yes. So this is quite silly choice, but the
other possibility could be to use the L3-4 basis.
I mean, if you make the point is, if you make full configuration interaction, then the difference will be not too large, but in fact we use in fact in this method once we make truncation, because then you can make truncation. So you can use this kind of expansion only included, for example, slated determinants that include single excitation or double excitation. So it means that from the reference wave function we only exchange one orbital, one single particle functions, or two or more. And then of course it starts to be crucial what kind of reference function we use. And when we use the truncated full configuration interactions, we use as the reference Hartree-Fock solution. So it means mean field solution for fermions. And then of course it starts to be important what is the reference. And we find that Hartree-Fock is quite okay, but only for weak interactions. And once you want to go to very strong interaction, then probably some other reference should be used, and it can work better. But this method is problematic because if you make this kind of truncation of full configuration interactions, then the method is not size consistent. So it means that if you take two systems that they are not interacting with each other, but you apply this machinery, then the energy of two systems is not the sum of these two systems. This can be a problematic if, for example, you are interested in the interaction about interaction between two systems, or you want to investigate different parts of the systems at the same time. So the solution.
This should be cured easily by assuming that every slated determinant has a block diagonal flow, namely that there's a block of left and block of right part of the system.
If you can, but but once you, but for example, you can imagine the situation that you have these two systems and some weak interaction between them, and then you have, then you can, in weak regime you can apply perturbation theory that will be still size constant, but I can imagine the regimes and this kind of regime, for example, interaction between two atoms. So interaction between two atoms at short range is exactly that you cannot, this method, the truncated interaction method will be problematic. You cannot apply perturbation theory because it will diverge or it will, so, and then you need the method that is psi consistent, because in fact what you really need is interaction energy. And the solution for this, for example, is coupled cluster method. The coupled cluster method is the method where we present the total wave function in the form with the exponential excitation operator. So again, our reference is the Hartree-Fock mean field solution, and we apply this kind of excitation operator where T is the sum of the single excitation, double excitation, and so on, and we can truncate this method at some level. And of course, higher we truncate it, then the method will scale worse with the number of single particle basis set.
Is e to the power of T unitary?
Yes. No.
If not, then
No.
change the spectrum.
No. Yes. So the point is that it's not unitary. Yes, I'm sorry. Yes. So.
It's happy to change the spectrum because the spectrum is related to phi is wrong.
Yeah, I want, because this is mean field solution, so I want to find the new spectrum with different, and then of course, in our parameters in this method, there are included in the excitations. I didn't write.
And I have another question.
So,
how do you know that the right way of expansion goes to the exponent of this T?
I mean,
some other function.
No. This is guess. This is like this is one of the possibilities, and it was found that it works quite well. And the reason why it works quite well is because this includes all single and double. Once you expand it in the form, of course, if you include all possible excitation, it's equivalent to full configuration.
I'm not questioning this. I'm questioning these factors that come from the expansion of the exponent compared to some other analytic functions.
No, so I mean, I think this was just numerically confirmed that it works quite well. I think that probably there is no rigorous proof that this is better. But I mean, why it's useful for us? I mean, of course, exponent has nice property that the sum of the excitation operator here gives the product of exponent times exponent, and this is something that is quite hard to get in other representations. But in yes, but in our case, so what's giving the results much more accurate compared to full configuration interaction truncated is that it includes this kind of representation, includes all the form of single and double excitation, for example, and then all the powers of it, because this is higher terms of exponents. So we have then all possible powers of single and double excitation, or all possible combination. And what was found for atomic or molecular systems, that this kind of part of wave function is quite important and gives much better results. Okay, I'm a bit close to finish with time, but okay. So first, I will present the convergence of this full configuration interaction with the basis set size. These are the results, just to show that really the convergence is very slow. So this is the convergence. This is the error of the exact diagonalization calculation with some finite size of the single particle basis set, and we can see, and in fact we are the calculations for the 6 particle systems, they are finished. What is the maximum possible for the maximum possible basis set that we can employ? So just for this calculation, the calculation took like 2 or 3 days for single point, and we can see that for relatively large or even intermediate interaction strengths, the error can be as large as a part of the omega of the harmonic frequency. So it means that the error can be quite large. And then applying the interpolation formula that we find can really improve the convergence and improve the results. And where especially this is problematic, so once we look on the unitary limit of interaction, it means that where G goes to infinity or is very large, is very important for ultra-cold atom physics, because there is quite many universalities in these systems. And then when we look how the spectrum of 4-particle system, example system of 4-particle systems, 2 spin up, 2 spin down looks like, we see that for the finite basis set, there is some unphysical crossing of state, at some finite number of interactions. This crossing should be at g going to infinity, so at 0 here. But unfortunately, for any finite number of basis sets, we get it at some wrong position. But then, when we apply our interpolation formula, these are the points, the black points. We can really extrapolate the results from few calculations for few finite basis sets to quite accurate prediction that agree quite well with this unitary limit obtained from perturbation theory. So the reds, they are correct only in this regime, and we see that there is quite nice agreement where it should be. Okay, then I maybe they analyze the convergence of this calculation depending on the number of excitations, the number of Slater determinants that we had in our wave function expansion. So we see that already the single and double excitation, they reproduce 95-98% of correlation energy, so it's quite well. But because I don't have too much time, maybe I will go to some. Excuse me. Yes, so just if I can have 3 minutes to present very nice results. So we applied our machinery, and we look on the total energy of this spin of the system of Fermi atoms, that the number of spin up and spin down is the same. And we properly scaled the total energy and interaction strength. And once we scaled the total energy of the systems by the Fermi energy without interaction, and properly scaled the interaction strength with the number of particles, we find this extremely nice universality. So these are energy obtained for very different number of particles. And once they are properly scaled, they really go onto the one line. So it means that the analytic regime for two particles, this is the black curve here, and thermodynamic regime obtained with the local density approximation here, they are very, very similar. So when we look on the difference between these two curves, in like when we enlarge it, we see that the difference and the maximum is only 4%, and this can have quite important. This is quite important because it shows that in fact any properties of the many-body system in this kind of regime is quite well described by the two-body properties, and only very small correction from higher terms of higher terms are important. When we look with our methods on this plot, like looking how the results converge to this thermodynamic limit, we see that our numerical approach converges quite well to the thermodynamic regime obtained with local density approximation. And in fact, it also confirms that local density approximation applied to fermionic systems entrapped in 1D works quite well, because there is not so, because of course there is people.
By local density approximation, you mean Thomas Fermi?
Yes, in this way, yes. But we are not in the perturbative regime, because once we compare our calculations with the just perturbative approach, we see that the perturbative regimes for this interaction strength that are presented here, they don't coincide with our points. So it's really strongly correlated systems, and our method was needed to do this. And the last slide where I present the last results is we tried to reproduce BCS pairing gap for this system, and also we did the calculations for few particles, and now we find that it converges much slower to the thermodynamic regime. So in the thermodynamic limit, for the positive interaction strength, there is no pairing gap, and for negative interaction strength, there is some exponentially dependent on the interaction strength pairing gap, and we reproduce quite well. Now the convergence to the thermodynamic limit is much slower because we need much larger number of particles, and we are still far away. But these red squares, they are the results of extrapolation from our results, from our numerical result, and we see that they are perfect. They perfectly agree with the analytical solution for the thermodynamic limit. Again, applying local density approximation. So this is this graph, or at the same time. And confirm that our method works quite well, and at the same time that where we are converging, the thermodynamic limit in our calculation is exactly the same that is obtained with the local density approximation. Okay, so just to sum up the part 2, we successfully applied applied the quantum chemistry method to describe cold Fermi atoms in traps, and some interesting application can be found. In 1D, yes, in 1D. It's very important because in higher dimensions there are other problems. If there is maybe someone interested in starting PhD studies, I'm looking for a PhD student for the project with Maciek Lewenstein within the homing grant from Foundation for Polish Science. It will be about quantum simulations, computations, and sensing with novel quantum molecular systems. So we want to apply some molecules to realize new technology, new quantum technologies. Okay, thank you very much for your attention.
I was asking Professor Berlinski to finish, to substitute for him at the end. He had to leave. We have time for some questions, even though we have some during the time. Who wants to ask something? Yes.
It's shown that this method, plastic method, is working well for short-range interaction, but can you use it for other kind of interactions like 1/r cube?
Yes, because in fact, in the electronic system, the interaction is Coulombic interaction, so it's 1/r. So it means that it will work for all interactions between point interaction and 1/r. Yeah.
The question is, it's working still so nicely, or?
I mean, for
I guess it's explored. 1/r.
yes, for 1/r it's explored. I don't think that people explored it for some intermediate force. I think that probably.
Coulombic interaction.
Yes.
It's not 1/r.
Yeah, of course. It's in 1D. All interactions are delta. Yes.
Yeah, but then all these others are approximations.
So and how this method will work in higher dimensions with the contact interaction, we don't know yet because there are some other problems.
Some interesting problems.
Yes.
More questions? Let me ask one final question myself. You see, if I understand correctly, what you call, and I try to confirm it, what you call a local density approximation is the Thomas Fermi approximation. Now, this Thomas Fermi approximation in 1D is pathological because nobody knows how to define so-called gradient corrections. So it is a little bit puzzling that you consider this result as some correct thermodynamic result. There is a little bit of a question mark about this.
But why do you need? Of course, then once you include.
Because it's in homogeneous system.
Yes, but
It's a non-uniform system, I should say.
yes, it's not uniform, but
Because of that, gradient corrections are necessary. Well,
I mean, yes. The point is that yes, of course, when you look on the wave function in the local density approximation, you don't have any oscillations that are on the top wave of the wave function. But still, this is the result that we obtain, and it's because once you look on the but of course it's not correct.
whether it's
No, but it's not.
reliable.
So I think that for few particles, it's not so accurate. But once you go to larger number of particles, then the shape of the cloud start to be reproduced quite well, I think.
Okay, there is a problem there.
Okay, we can.
If no